Okay, this is the section for week 13. Today we'll mostly be talking about the things that we talked about in lecture this week: time series data, data that vary by time and also by unit, and instrumental variable selection models, those sorts of things. So there's a zip file on Courseworks that has most of what we need for today. In addition, you need to install the R package called sample selection that has a little s to start with and a big S in selection. That does some maximum likelihood estimation of Heckman and Tobit models. But before we get to that, let's just start with plain time series that's generated by an autoregressive of order 1 process. And so that can be done just by using the functions that are already available in R, in particular the ARIMA sim function. So we're going to simulate an AR process of order 1 that has the autoregression coefficient of 0.9, 30 time periods, and we generate a Y like this. Another pack, I don't know if T-Series comes standard with R. I think it does, but if not, you need to install that also. So let me modify this. For a frequentist, sort of the first thing that you would do in a situation like this would be to test the null hypothesis that the data generating process is stationary. However, for most of the time that you might do this, you would fail to reject a null hypothesis that the data generating process has a unit root, even though in this case it is actually stationary. However, it's relatively close to having a unit root because the population coefficient is 0.9. So this is essentially a test of the null hypothesis that autoregressive coefficient is 1. And a lot of times with only 30 time periods, which is probably about reasonable for the number of time periods that you might have for annual data, then you would fail to reject that null hypothesis. And so it's kind of a, from a Bayesian perspective, odd thing about frequentist practice. You know, no one really believes that autoregressive coefficient is exactly 1, but in order to proceed with the typical estimators and stuff, you first have to be able to reject what no one really believes in the first place. You could do a different test that takes the null hypothesis to be that the data generating process is stationary, and the alternative hypothesis to be that the data generating process has a unit root. And I think in this case, you would probably fail to reject that null hypothesis also. And so if you're in a situation where the number of time periods that you have is so small that you would basically fail to reject the null hypothesis, even regardless of what the null hypothesis is, or the possibility that the null hypothesis, they have different null hypotheses that are mutually exclusive. And then that dictates what estimators you can use after, I think illustrates that, the supposed claim by some people who are pro-frequentist that, they're not expressing their beliefs about the data. And particularly in the case of time series, it sort of shows that to be particularly false. I mean, it's always true when you specify a likelihood function, you're specifying your beliefs about how the data were generated. But if you're going to do some sort of a null hypothesis test before you do the rest of your analysis, it matters which null hypothesis you specify, whether it's stationary or non-stationary. And if the choices that you're going to make in terms of your estimator depend on whether you reject or fail to reject that null hypothesis, then you're basically expressing your beliefs in terms of a null hypothesis. So if you're going to express your beliefs that you think this is stationary, that is essentially the same as the Bayesian approach, where you put a prior on this autoregressive coefficient that's between 0 and 1. So I don't think there's really that much of a difference between what time series frequentists are doing in practice and what Bayesians are doing when they specify prior beliefs about these parameters. But the way in which these get estimated certainly is different between frequentist and Bayesian stuff, although in a lot of cases when you have autoregressive coefficient that is close to 1, the frequentist estimators are not particularly good when you only have a number of time periods of 30. So that's that. And then the next question is, how would we do this in STAN? So we're going to need a list of data that takes into account the number of time periods and the series. And I've started to write a part of the STAN program here to get you going. So as usual, we have the data block where we're just going to read in the data. The number of parameters to estimate are rho, which in this case we're going to restrict to be between 0 and 1. In principle, autoregressive coefficient could be negative, but that implies, basically wild switching of the series that's inconsistent with most things that we think we see in social science. And so given that we're willing to assume that rho is between 0 and 1, we can have a prior on the period before the initial period, here denoted y0. And we also want to estimate a mean for this data generating process and error standard deviation sigma. So we talked about this on Tuesday. So basically the model, we need to build up the expected value for y with a loop. And then it's just a normal likelihood for y, but we have an additional consideration. We need, depending on how you look at it, a prior for the period before the initial period, or this is just the first piece of the complete data likelihood if you consider the period before the initial period to be missing data. And then another thing that could be considered missing data, what if we want a 1 period ahead prediction of what this series would be? That is going to entail drawing from a normal distribution. And you guys just need to figure out what would be the constructions for the y hat, the prior on y0, which we talked about on Tuesday. This, we'll put it in right now, is normal with mean mu and standard deviation, the square root of 1 minus rho squared times sigma. And that, in addition to being what we talked about on Tuesday, is pretty intuitive in that if you have a correlation very close to 1, then you know with a lot of certainty what the period before the initial period would be, because it has a high correlation with whatever the y1 period is. So why don't you try the rest of that?
The prior on error term is mu sigma, like normal mu sigma. I mean, so they generate the process will do something like raw multiplied by previous period plus some random error.
Right. So if this were unknown, then you could basically do matrix sort of stuff where you add a random error and multiply it and shift the whole thing over. Here, we're talking about data, so there's no transformations. We just need to make a vector for the expectations of y, and so those are going to be exclusive of the error. So you just need the systematic part. Fourth line. Yeah, you could do this. So that basically just entails calculating the mu times 1 minus rho once, which is the intercept of the linear predictor, And so for the first period, the expectation is going to be the intercept plus the value of rho times the realization of y0. And then for the subsequent periods from 2 up to t, then the expectation is going to be the intercept plus rho times the previous realization of y. So the somewhat tricky thing here is that these y hats are autoregressive with respect to the y, the realization of the outcome. They're not explicitly autoregressive with respect to the previous y hats, although the y hat is relevant to the y at time t. And so if we have those lines, then that covers us for the model block, unless we want to specify some priors on mu and rho and sigma. You know, as usual, we probably do increment from Jeffrey's prior probably for standard deviation. It's not going to matter that much what your prior for mu or rho is in this case. So if that is what we need to do for the model block, then what do we need to do to get a 1 period ahead, express our beliefs about what y is going to be in the first period after the period where our data stops? Yeah, pretty much the same thing. So y next is going to be, we have to use the normal random number generator rather than the normal density here, but it's going to be something like that. And if we wanted express our beliefs about multiple periods ahead, it would start off this way, and then it's going to the systematic component is going to depend on the realization of the previous draw from the normal distribution. And consequently, if you go out enough periods, you get very uncertain about where a series like this is going to be. So if we have that, then we have our data. Yes. And so we can get the posterior distribution. All right. So in this case, it actually estimated rho to be on the boundary. That can happen. It's not what you want to happen, but considering the true data generating process is 0.9, and we expressed our beliefs that rho was bounded between 0 and 1, it's not inconceivable that something like this would happen, that would, maybe cause you to adjust your beliefs about what you think the data journey process is. Gotcha.
Yeah. Why did we use YT to predict Y hat T? Shouldn't we use like T minus 1?
Oh yeah. So that would make a difference. Yes. So did we get it right the other way? All right. Do over on the stand model.
And the same goes to the generated quantity probably. No.
That's the right one.
There is.
Yeah. All right. Do over. But in any event, that could actually happen even if you didn't have a mistake in your code. Particularly if you express a uniform prior belief about the autocorrelation coefficient. If you express a beta distribution that has a mode somewhere in the center, then you're putting probability 0 on rho being exactly 1. Whereas if you put a uniform prior, then the value 1 is just as reasonable as any other value in the 0 to 1 interval. And so now we actually get value of rho whose posterior mean is 0.83, but whose interquartile range definitely includes the true value 0.9. You may have gotten something a little bit different, but in any event, we get posterior values of the initial period or the period before the initial period, the next period after the data stop, mu, rho, etc. The R hats look good. The effective sample size looks good-ish. Probably look fine if we do the dependence plot. So might want to tweak the settings here. Seem to have a fair amount of divergence, which is not completely unexpected when a rho gets very close to 1. So, we've restricted it to be between the 0 and 1 interval, but, there's certainly a tail of the draws where rho can be very close to 1. So, either putting some more prior information about rho or by increasing the target acceptance rate with the adapt delta setting to make it take smaller steps when doing the Hamiltonian thing could eliminate that problem, I'm sure. So Stan, in other words, shouldn't have any particularly difficulty sampling from a model this simple, or even models that are more complicated than this. Okay. So any questions about the AR1? No? All right. So the next piece is replication of a paper in political science. And these guys, Swank and Steinmo, have written a number of papers that have analyzed how changes in taxes on investment or other liberalization of restrictions on investment from foreign countries. If, for example, the United States decreases its tax rate on, profits and stuff from foreign companies, then does that induce Canada to reduce or to change its policies, et cetera? Because, a lot of companies deciding whether to invest in Canada or the United States would consider those sorts of things because, and things like that, because the United States and Canada don't really have tariffs to speak of. So you could, start your subsidiary in Canada and export to the United States, or you could start your subsidiary in the United States and produce here and export to Canada, whatever. So there's some data in the zip file called tax data. And if we can just look at some of those, just see the first 6 observations here. They use some weird names. The outcome variable is like capital taxation. And they use 1 period lags of some variables in making the model. It's some comparative political economy thing. And so their model in the paper could be estimated by this these squares thing, and then you could go on to calculate panel corrected standard errors. And one thing that they did, which we'll talk about later, is because they only have 15 time periods, and because including a lag dependent variable is biased for finite t, they've actually chosen to instrument for the lag. So what here appears lag 1 tax rate is actually the predicted values from an instrumental variable model for the lag tax rate. And so I think it's not exactly equal to the tax rate in the previous period, but that is not too essential. If we were doing a frequentist thing, then we could estimate panel corrected standard errors. It might be nice to have more than 15 periods, but in any event, our focus today is how will we estimate a model like this in STAN, taking into account that the error terms certainly can be correlated within country over time with just, for example, an AR1 process like we talked about previously, but also there's reason to think, and it's actually the theory, or it's not exactly Swank and Steinmo's theory, but it's a theory that they talk about in the paper, that you should see dependence across countries because, the OECD countries, or at least the 13 most important advanced economies, compete with each other for investment, and tax policy is one of the things that they alter to do that. And so if we look at the STAN code for this, I created a Kronecker function to do the Kronecker product, which we can talk more about in a little bit, but the essence of the STAN program is like this. As usual, we have the X data, the Y data, so forth. The parameters to be estimated are the coefficients on the X's, the row parameter for the autocorrelation within country over time, and then we're going to have a correlation matrix and standard deviations for so these error standard deviations, there's 1 per country. And then, so there's N countries, where N here is 13, I believe. And then, so there's a standard deviation of the errors for each country. There's also an N by N correlation matrix that is intended to capture how the errors are correlated across countries. So certainly, the Canada and the United States might have a high correlation. Australia and New Zealand might have a high correlation, but the correlation between New Zealand and Canada is probably not so big. In any event, we want to estimate what those correlations across countries and the errors are. This is the sort of thing that frequentists do in 2 steps. They'll use least squares to estimate the coefficients. The coefficients are estimated consistently, even if there is autocorrelation and spatial correlation in the error terms. If the coefficients are estimated consistently, then the residuals are estimated consistently, and they can use the residuals to estimate the cross-country error covariance matrix. But in Stan or in Bayesian generally, there's no 2 steps. You just have to estimate all the parameters at once. And in this case, we have the additional consideration that presumably the errors are correlated over time. So we need to make a covariance matrix for an AR1 process that's here assumed to be common to all the countries. And then we're going to compose the error covariance matrix for the entire sample as a Kronecker product of an AR1 covariance process within country and this n by n covariance across countries. So how we do that in the model block, again, we can make this 1 minus rho squared thing. And then as we talked about on Tuesday, for AR1 process, the correlation matrix is very simple. It's just rho raised to the absolute value of the difference between the row index and the column index. So that will put ones along the diagonal, rho raised to the power of 0. Just above and just below the diagonal, we have rho raised to the power of 1. If we go farther away from the diagonal, we have rho raised to the power of 2, etc. All the way in the top left and the bottom right corner, we have rho raised to the power of n minus 1, or t minus 1. But we want not the correlation matrix here. We want the covariance matrix, and covariance is the correlation matrix multiplied by sigma squared divided by 1 minus rho squared. But we're going to basically just set sigma squared equal to 1 here and estimate the sigma squared from the cross-country part. So we would have an identifiability issue if we were estimating a time error covariance, and for each country a cross-country error variance. So that just means we're just going to be dividing by 1 minus rho squared for each of these terms. So that constructs the theta matrix, and theta matrix, although it's capital T by capital T, only has one unknown parameter in it that it's a function of, and that's rho. So this is why I said on Tuesday that the usual thing that we do for correlation matrices, with the LKJ and stuff, is not really the most appropriate thing for correlations over time, because the LKJ is for a general covariance matrix where we're going to be, estimating K choose 2 correlations that can just be completely unstructured, aside from the fact that this has to be a positive definite matrix, etc. In the particular case of correlations over time, we have, reasonable beliefs about additional structure, such that, that entire T by T matrix, and for an AR1 process, it's just, one unknown scalar parameter to it. If it were AR2, then it would be more complicated, but again, it's still not, just estimating T choose 2, basically unstructured correlations. We have more strong beliefs about how a correlation for a process over time than we do for a general process or a process across space. And so then we can construct the covariance matrix that's NT by NT for the entire sample, which we called sigma, which basically entails, because the data here are sorted by time period and then by country, Kronecker producting, if that's a verb, the AR1 covariance matrix for the within country dependence, and the Kronecker product with the covariance matrix for the cross country dependence, where in this case we're going to have diagonal matrix of standard deviations multiplied by an n by n correlation matrix multiplied by a diagonal matrix of standard deviations on the right. And that involves the Kronecker function that I mentioned above, and I'll talk about that a little bit more in a second. But then the likelihood is just going to be, x times beta for the entire sample. And now we have a y that's nt by 1, and x times beta that's nt by k times k by 1, so resulting in an nt by 1 vector, and an nt by nt covariance matrix for the errors. And so this sort of way of looking at it, I guess some people would say, well, you're estimating a giant covariance matrix that's nt by nt, but it's a function of just, one row parameter and, n choose 2 correlations and n standard deviations. And so for reasonably large t, that shouldn't be a particular problem. And even if you had not such a large t, then proper priors can compensate for that. So we have some halfway plausible priors here. Just going back up to the Kronecker function. Unfortunately, Stan doesn't have one of these built in to it yet, so I had to write one myself, which is kind of ugly, but basically it just does what the Kronecker product operation is. If you have two matrices A and B, take every scalar in A, multiply it by the entire B matrix, and then stack up a whole blocked matrix where each block has the matrix B multiplied by the corresponding scalar in A, and you get a NT by NT matrix out of that. Yes?
So just to get this thing, we estimate one row that's the same for every country, right? So we assume that this R1 process is the same within every country.
Correct. We could do some sort of a hierarchical prior with that, estimate a different row for each country, maybe shrink them toward a common mean, etc. That would entail not a Kronecker product at the end, but we would actually have to multiply B by different A matrices, which is to say multiply our, upsilon sigma thing. We would now basically have not just a single theta matrix, but a theta matrix for each country. And it would depend on this. So this would be like like that. And then we would have to do it separately for each. And then multiply them in the right way to get the whole thing. That would be more of a mess, but it would be a better model probably for predictive purposes. Anyway, so we could estimate a model like that. We're not actually going to do so. But just before we go on to the IV stuff, it's worth taking into account that probably modeling the dependence and the errors is not the ideal way to go about talking about the hypotheses that are being discussed in the original Swank and Steinmo article, because you can do all this stuff modeling the errors, but you're still making the assumption that the errors, although dependent over time, possibly dependent across countries, are independent of the predictors, which is a pretty strong assumption to make. And so probably the better thing to do would be to incorporate the spatial thing into the systematic component of the model, so that those things can be correlated with the predictors, can interact with the predictors, etc. That would involve, for example, a spatial lag model, like we talked about at the beginning on Thursday, where you have to specify or parameterize cross-country weights matrix that, in a manner of speaking, kind of serves the same function as the upsilon in this, but the cross-country weight matrix is not a correlation matrix. It's actually a stochastic matrix. So instead of having the correlation structure, it has the structure that the rows are non-negative and they sum up to 1 for all that. In any event, we gave it sort of an example of sketching out kind of how to do that on Thursday from a Bayesian perspective. From a frequentist perspective, you have to consider the weight matrix to be fixed, basically, unless you had a huge number of time periods. And so that leads people to do things that probably seem a little bit arbitrary, like, if countries have a common border, then they have a weight that's not 0. And if countries don't have a common border, then they have a weight of 0. And that gets a little bit, it's a little bit arbitrary to begin with, but then you have, what are we going to do about, islands? So New Zealand technically doesn't have a common border with anyone, but for the purpose of this, we'll say it has a common border with Australia, and the same thing with like Iceland, and what do you do about that? So probably the more plausible, reasonable thing to do would be to estimate the weight matrix along with everything else with the Bayesian fashion, and put some reasonable prior information in the form of Dirichlet's on the rows of that matrix. But we're not going to do that. We're going to move on to instrumental variable stuff. So these are the data that are talked about in Lancaster. They originally came from an article about does compulsory school attendance affect schooling or earnings? And you can download that data from the Wiley website, but basically we have log wage, we have number of years of schooling, we have the quarter of the year in which the person was born, and we have their age as of whenever the data were collected, probably around 1990. And so the theory of this here, in the United States, the school policies are largely determined by the states, or maybe even by the school districts. And they have essentially arbitrary rules about when you can start first grade. So you have to be like 6 by September 1st, but some school districts say you have to be 6 by July 1st. And then other school policies, they have sort of rules about when you can drop out from high school. So you have to be 15, or you have to have completed 9th grade. Basically, because we don't have much of a federal education policy, we just have a big mishmash of rules pertaining when can you start school and when can you first drop out of school. And this plausibly gives some exogenous variation. And that there are some people, if they were born just a little bit earlier would have been allowed to enroll in first grade of basically 360 days previous, and then they, would have been able to drop out earlier if there was some rule about, you have to complete ninth grade before you can drop out. Other people, were born a little bit later and they happen to live in a school district which says you have to be age 15 before the start of the year before you can drop out. And so they have to get basically a year more schooling than they wanted to get because their birthday was, not quite early enough, et cetera. So the idea of the original paper is to use the quarter in which someone was born as an instrument for the number of years of schooling that they get, and then estimate the effect of schooling on wages through that. And so in terms of how we would do this in STAN, the data, so we have some number of observations. We basically have 2 Ks, the number of predictors you're using in the model for the treatment, which in this case is the number of years of schooling that you have. And the other K is how many variables you're using in the model for wages. So anyway, that's that. Then we have a vector of treatments, T, and we have a vector of outcomes, Y. So we want to estimate the coefficient on the instrument, which in this case, well, I should have separated these out. In any event, we want to estimate the coefficient for the instruments. We want to estimate the coefficients for the other control variable, which in this case is just age. And we want to, so Z in this case is going to be 4 columns, depending on what quarter you were born in, dummy variables for that. And then we need the reduced form coefficients, beta star. And we want to estimate the treatment effect delta. We want to estimate the correlation between the 2 errors row, and we have standard deviations for each of these processes. So hopefully I remember to put the likelihood for something like this. So we have that here. So we can decompose a bivariate normal likelihood as a marginal normal model for the treatment, which in this case is years of schooling, and a conditional normal model for the outcome, which is log wages, conditional on years of schooling. And so the first is pretty straightforward. The second, we're going to use the reduced form of the model where we use both the X's and the Z's to predict Y, but the coefficient on Z is equal to delta times the vector lambda. And then there's an additional piece that goes into the systematic component for the conditional model that basically involves the ratio of the error standard deviations, the correlation between the error terms, and the residuals from the first term, and then the conditional standard deviation is scaled down by the square root of 1 minus rho squared. So in this case, there should be, did I bring in the X? I can't remember. Yes, so gamma should be actually a vector of length 4 in this case. Is that how I said it? It's going to be a vector of length 2. And is the coefficients on the instruments. So let's give that a try. So basically, to do this in Stan, just need to specify the univariate normal model for the treatment, conditional normal model for the outcome, and priors on, if you want to, on these parameters here. So I'll put that back up. So just to get started, might need something like this. Now you could just estimate the bivariate normal likelihood using multivariate normal, but that's going to be a little bit slower in Stan because it doesn't have a bivariate normal likelihood specifically. It's just using the general multivariate normal likelihood, which isn't nearly as optimized in Stan as the univariate normal likelihood. So this will probably go faster, but this is just another way of decomposing a bivariate normal likelihood into a univariate normal margin and a conditional normal distribution. So go like this, basically. Okay, starting to get a little short on time here. So did everyone get something that looked like it would ultimately end up like this? Basically, we just need some local vectors for the expectation. The residuals of t will make the expectation of t as a function of the covariates and the instruments. Create the residuals just with subtraction. We have a plain marginal normal model for t, and then in the conditional normal model for y given t, we have the covariates. We have the reduced form expression where this actually depends on z and multiplied by the vector lambda and multiplied by the scalar delta. Scalar delta is the treatment effect that we're interested in. And then we have an additional piece that comes in from the residuals of the first part of that model. So let's try to run this without any prior information. We got the data. All right. So we need to create a data list that I think looks like this. And then we can do stand. That was wrong. All right, so we can attempt to run this in stand. Need semicolons. Still need semicolons. What? Oh, come on. So this one is going a lot slower. Go faster. Go faster. It's a more difficult model for Stan to adapt to and to get reasonable draws from the posterior of, particularly because in this form we're not expressing any prior information about anything except for a Jeffreys prior on the sigmas. Where are we at? Come on. Okay. We might have to actually skip ahead, but when this finishes, I wanted to make the point that the posterior distribution of delta and the posterior distribution of the elements of lambda may very well have a high amount of posterior dependence, which can make it difficult for Stan to work around. So basically, there's a lot of information in the data potentially about the product of delta and lambda, but less information in the data about them separately, because that basically depends on how much information you're getting in the model for treatment assignment as to how closely associated your birth quarter is to the number of years of schooling that you get, which, although it might be a valid instrument, is probably not one that is particularly strong. So, if I told you, here's some person that was born in the fourth quarter, how many years of schooling do you think that they would get? Most people would just be like, well, whatever is the mean number of years of schooling for, their area or something like that. They probably wouldn't even take into account that, the thinking that goes behind this particular instrumental variable. So it's probably not a particularly strong instrument, and that was actually demonstrated in the Lancaster chapter. And when you don't have a very strong instrument, then it's going to be difficult to get precise estimates of the treatment effect. And you may get a posterior distribution that doesn't look so good, or that takes an extraordinarily long time to get there. All right, so that looks like it might not finish. The last thing that I wanted to do today, which we're not going to have time to do, is a Heckman model. And so this is very similar to instrumental variables, and you can probably do this on your own. In the sample selection package, it has the capability to estimate these by maximum likelihood, and that usually has a terrible sampling distribution. But in this case, estimating a model for how much women in the 1970s would earn, as a function of how much experience that they have, and that, and their education and whatnot, and all that sort of depends on the process by which women select to be in the workforce or not. You can estimate that by maximum likelihood. In particular, the standard errors can be very sensitive to what algorithm you use and all this, but the likelihood is reasonably easy to write down. It's very similar to the likelihood for instrumental variables model, in this case with binary selection into treatment. And you could use priors and get the posterior distribution of those parameters with Stan, hopefully pretty easily, but probably not before we have to get out of here. So did this actually finish? Yeah. Is it close to finishing? Not particularly. Okay. Well, I'm just going to stop this. But trust me, if you actually got the posterior distribution of that instrumental variables model, it might not look particularly good, because there's not a lot of information in the data with which to estimate this treatment effect. And that's sort of an inherent issue with the data generating process, but it's an issue that can be exacerbated by frequentist techniques that are only asymptotically valid when you have a finite sample. And it's an issue that can be mitigated if you specify informative priors in a more nuanced way to hopefully get a little bit better separation of the parameters in the posterior distribution. Okay, so that is it for today.